Hello learners, welcome to Unacademy. Just give me 1 second, I'll check if I'm online. Alright, welcome back to the session. So in today's class we're going to learn what is collusion, what are the types of collusion, and especially what happens to the velocity. We're going to derive the equation for velocity of two objects when they are actually in one-dimensional elastic collusion. Alright, so before we begin, my name is Mohana. I'm a physics educator here at Unacademy. So this is my Telegram channel. You can actually follow me on my Telegram channel. Before any class goes live, I would be posting the link here. And also this is Unacademy ICSE board and ISC board common Telegram channel. So you can join this channel as well. Alright, and okay, 1 second guys. Okay. Now, with this note, let's begin. So, whenever we talk about collusion, right? For a collusion to take place, it is not necessary for two objects to actually physically collide against each other. Even if the path of one object is affected by the force exerted by the other, then also we say that particular object has undergone collusion. For example, if you take alpha scattering experiment, so what we have is actually protons and neutrons in the center of the atom, right? This forms the nucleus of the atom, and around it we know we have electrons. But let's say we have an alpha particle, and if this alpha particle is a positive charge, and let's say this alpha particle is made to collide with this particular nucleus over here. So this is a positive charge, and what we have over here is also a positive charge. So this charge that comes, this particular charge that is alpha particle that comes towards this nucleus of the atom, right? It will not, as far as it reaches one particular point over here, right? These two particles are basically positive in nature, right? So this will basically be repelled by this charge of the nucleus, and it would change its path. Right, so even this is actually called as a collusion. So for a collusion to happen, the path of the two objects doesn't necessarily have to collide against each other. Physically they don't have to collide against each other. Even if the force exerted by one object influences the path of the other, then we say collusion has taken place. Now this collusion is of several types. So if you see, the first type we are seeing is an elastic collusion. So let's say you have the example that I gave right now, okay? That is the alpha particles getting the collusion, the alpha particle in this case. That is, in this case, if I take any collusion between subatomic particle, alright? Or if you take collusion between two glass balls or ivory balls, alright? All of those are elastic collusion. In an elastic collusion, if you see, kinetic energy before collusion and after collusion, there is absolutely no loss in kinetic energy. Okay, such a collusion we call it as elastic collusion. Now the next type we see is actually inelastic collusion. So in inelastic collusion, if you see, there is a loss in kinetic energy. So let's say collusion that happens between vehicles, if you take, right? So initially if you say the vehicle had a velocity, but has a particular velocity, but after collusion the velocity can change, but it obviously reduces, or it can actually become zero, right? In this case what we are saying, kinetic energy of the object is actually changing. So such a collusion is called as inelastic collusion. Next, what we have is a perfectly elastic collusion. Let's say we have a person here, and he has let's say we have a person, okay, this person here, let's say he actually runs and jumps into this trolley, and then let's say the trolley and the person moves as one single system over here. Alright, so what we see over here, initially the truck or the person had different velocities, right? But after the person jumps into the truck, both the person and the truck move with one single velocity. That is, if after collusion, if the two objects tends to stick together and move as one single system in the sense they tend to move with the same velocity, then what we have is a perfectly inelastic collusion. Alright, that's the difference between inelastic collusion and perfectly inelastic collusion. In perfectly inelastic collusion, the two objects tend to stick together and move with one single velocity. Now what we have is a superlative or explosive collusion. In this case, there is going to be an increase in kinetic energy. Okay, when actually a bomb blasts, when you burst crackers, right, what we see is basically a superlative or explosive collusion. Now next what we have is a head-on or one-dimensional collusion. Very simple. Any collusion that you see, okay, if it is going to happen head-on, right, like or if you see, if the collusion that tends to happen in one direction, right, in one dimension, uniform line over here, right, in one dimension, then we call it as head-on or one-dimensional collusion. Okay, so in this case what we see, the objects that are colliding, they tend to move along the same path before and also after collusion also they tend to move along the same path. Okay, then what we have over here is very simple. Okay, in this case next we have is an oblique or two-dimensional collusion. So if you see, when you hit the striker with the carom coins over here, the carom coins tend to move on this plane over here, but they move in different directions on this carom board, right? So this is an example of oblique or two-dimensional collusion, right? In this case what happens is the objects, they do not move along the straight line path, but they move on the same plane. Such a collusion we call it as oblique or two-dimensional collusion that happens in two dimensions. Okay, so this is an example of two-dimensional collusion. Now what we are going to see is basically elastic collusion. If you see, when we see an object has elastic collusion, is basically if there is no loss in kinetic energy during a collusion, then we call it as elastic collusion. That is like collusion between subatomic particles or collusion between glass balls or ivory balls, right? So in this case, if you see, like even if they are coming towards each other, or if they are going one after each other, and if they are colliding, actually collusion between such particles, we call it as elastic collusion, mainly because the momentum is conserved in such a case. Total energy of the entire system is conserved. Kinetic energy is conserved again. So kinetic energy before and after collusion is same. Okay, is conserved actually. And if you see force involved during this collusion, if you see, all of them are conservative forces. Now mechanical energy in this case is not converted into heat, light or sound, etc. Okay, so these are the characteristics of elastic collusion. Point to be noted is momentum is conserved, total energy is conserved, total kinetic energy involved is also conserved. That is, mechanical energy is also conserved in this particular case. Okay, so in an elastic collusion, okay, which of the following is conserved? In an elastic collusion, which of the following is conserved? If you know the answer, you can give it in the chat box. In an elastic collusion, if you see, right, momentum, energy and kinetic energy, all of this is all of the above. All of the three are basically conserved. So now let's take elastic collusion in one dimension. Okay, if you see in one dimension, elastic collusion means the object are going in a straight line path. Okay, so they can come towards each other, or they might be going one next to the other. That's all right, but they are going in a straight line path. So that's why we have one dimension, and it's an elastic collusion, which means momentum is conserved and kinetic energy is also conserved. Okay, so let's take two objects over here. So let's see, these two objects has mass m1 and m2. Initially both of them have a velocity u1 and u2. Okay, now after sometimes they collide against each other. After collusion, if you see, the velocity associated with them changes. Now what we want to do is, what is this velocity? Okay, how much we are going to derive the equation for these velocities. Okay, so initially in this case, if you see, okay, if you see in this case, the energy, that is the basically in the first case over here, the velocity, the initial velocity of m1, that is of this particular object, okay, should always be greater than the velocity of the object 2, right? Let's take this as object A and object B. Okay, velocity of object A should always be greater than velocity of object 2 for collusion to occur. Why? if let's say u1 is actually less than u2, which means this object, where the distance this second object B covers is obviously greater than the distance object A would cover, right? Then collusion will never occur, right? Now if I say that the distance of right, now if I say the distance of the object 2 over here, the object B over here is less means, okay, is less means, so this is covering the distance it covers for a given time is less, but the same object over here, if I say velocity is more, means the distance the object covers for a given time is more. So obviously after some time it would actually be able to collide with the object B over here. Okay, so that is one point that to be taken into account. Okay, so now what happens is after collusion, if you see, particularly after the collusion, because it's an elastic collusion, because it is an elastic collusion, after collusion what will happen? Both the objects will actually get separated and then they would move in a straight line path, right? But for them to get separated and then move means, obviously in this case what should happen? The velocity of the second object should actually be greater than the velocity of the first one. In other words, velocity of B has to be greater than velocity of A over here. Right, so that is the only way these two objects will actually not stick together, but they will separate and then move together as one single system. Right, if they stick together and move as one single system, then what would happen is it will become a perfectly inelastic collusion. But what we are seeing, the derivation is for one dimension elastic collusion. Right, so they cannot stick to each other, so they will get separated. Okay, and after collusion, so if they are getting separated, means the velocity of the second object will be more than the velocity of the first object over here. Alright, now in any collusion, linear momentum is conserved. So even in elastic collusion, if you say, linear momentum is actually conserved. So if you say linear momentum of this particular system is conserved, means very simple. What we have is velocity, that is momentum is nothing but mass into velocity, right? Momentum of A, right? Initial momentum of A, that is m1 u1, okay, plus initial momentum of B, that is m2 u2, must be actually equal to final momentum of A, that is m1 v1 over here, plus final momentum of B, that is m2 v2 over here. Okay, so we got one equation over here. Alright, now what we are going to do is, we are going to take the velocities associated for object A on one side and object B on the other side. Okay, so let's take the momentum associated with object A to one side. So here we have m1 u1. Okay, then let's take this quantity to the other side. This will be minus m1 v1, which is actually equal to, in this side we actually tend to have m2 v2 over here, and take this to the other side, minus m2 u2. Okay, here m1 is common, so we can take m1 commonly outside, and you have u1 minus v1, which is actually equal to m2 into v2 minus u2. Okay, let's name this as equation 2. So this we got from conservation of linear momentum. Now in an elastic collusion, we also know kinetic energy is also conserved. Right, so let's write kinetic energy of object A. So kinetic energy of object A before collusion is nothing but m1 u1 square. Okay, kinetic energy of object B before collusion will be half into m1 u2 square, which is equal to, after the collusion, the kinetic energy again changes. So kinetic energy after collusion, if you see, in this case it will be half into m1 v1 square, okay, plus half into m2 v2 square over here. Half is common on all sides, so obviously that can be eliminated. Then what we end up having is let's take let's take similar quantity on same side, right? Then we have m1 u1 square. Let's bring kinetic energy associated with object A to one side, okay, which means to the other side let's bring minus m1 v1 square, okay, because half over here, if you see, let's take this as half over here, right? So which is equal to, on this side you have half into m2 v2 square minus half into m1 u1 square. This term we are taking it to the other side, right? This term we are again taking it to the other side. So we have the change in kinetic energy associated to object A on one side and change in kinetic energy associated to object B on the other side over here. Okay, now if you see, half is common in on both sides, so we can remove that, right? Also if you see m1 is common, so we'll take okay, right, m1 can be taken commonly outside, so m1 into u1 square minus v1 square we have on one side, which is equal to m2 into v2 square minus u1 square, right? Now if you look at this equation of u1 square minus v1 square, this is of the form x square minus y square. X square minus y square is nothing but x plus y into x minus y, right? So let's substitute for the same over here, right? Let's substitute for the same in this equation. Now what we get is m1 into, okay, u1 minus v1, which is into u1 plus v1, which is actually equal to m2 into, similarly this is also of the form x square minus y square, we can write it as x plus y and x minus y. So we have v2 minus u2, sorry, right? We have v2 minus, in this case, let me just quickly, I'm really sorry guys, over here this is actually u2, okay, this quantity is u2 over here, okay. So v2 minus u2 into v2 plus u2, right? Let's take this as our equation number 3. Alright, now what we are going to do is, we are going to divide this equation 3 by 2. Okay, so that is, this equation is 3 over here, right? Let's write that over here. That is, we have m1 into v1 plus u1, okay, into u1 minus okay, just a second guys, 1 second. Okay, we have this equation over here, that is m1 into u1 plus v1 into u1 minus v1. This is actually equal to m2 into, on the other side we have v2 plus u2, okay, and into v2 minus u2, right? This is equation number 3. Now we are going to divide this equation, okay, by this second equation we got over here, okay, by this equation over here. All right, so let's divide this by let's divide this equation we have by m1, okay, into u1 minus v1, okay, on the other side, right, on the other side we will divide by m2 into v2 minus u2. All right, so if you divide this equation on both sides over here by divide equation 3 by 2 if you do, right, m1 cancels, this term also cancels, you will end up getting u1 plus v1, which is actually equal to, this side v2 cancels, this term also cancels, we will have v2 plus u2. Okay, so let's take initial velocities to one side. So you have u1 minus u2, which is actually equal to v2, okay, minus v2 minus v1. u1 minus u2 is nothing but relative velocity, okay, relative velocity. This is basically relative velocity of A, okay, relative velocity, okay, of object A, all right, this is relative velocity of object A with respect to B, okay, before collusion, right? This is relative velocity, this is relative velocity of object A with respect to object B before collusion, okay. This will be equal to, this will actually be equal to v2 minus v1 is what? Very simple, relative velocity of object B, right, of object B, that is what is the velocity of the object B over here, v2 minus v1, right. So a relative velocity of object B with respect to object A, but this is after collusion, right. So from here we can say that the relative velocity of approach, that is, our approach is nothing but relative velocity of A with respect to B before collusion is actually equal to relative velocity of the object B over here, okay, that is the second object over here with respect to the first object, okay. Relative velocity, this is nothing but, that is nothing but the relative velocity of separation over here, Okay, so from here what we are getting, elastic collusion in one dimension. When we are seeing that the relative velocity of the objects before collusion is equal to their relative velocity after collusion as well. So velocity, the relative velocity of approach is equal to relative velocity of separation. Okay, so this, so from here if you see, how do we get V1 and V2? Okay, from here we just want to see how to get elastic collusion in one dimension, especially velocity of the object after collusion. How do we get the derivation for V1 and V2? That's very simple over here. What we are going to do is, we saw this equation, right? We have this particular equation, U1 minus U2 is equal to V2 minus V1, right? We got this before collusion velocity, relative velocity before collusion is equal to relative velocity after collusion, right? So from this if you see, let's take for V2. So let's substitute for V2. Okay, V2 is nothing but U1 minus U2, and this goes to the other side plus V1. Okay, now the first equation that we saw in this case, right? Right, so in this case if you see, this is basically V2, right? So now if you see, we got a first equation when we said linear momentum is conserved. We got this particular equation over here, that is m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2, right? So let's substitute in this equation. That is what we have over here right now. What we have is basically, when we said linear momentum is conserved, we said m1 u1 plus m2 u2, that is momentum before collusion, is equal to momentum after collusion, right? m1 v1 plus m2 v2. Now in this over here, from this relative velocity that we got right now, we will substitute for v2. We just said this velocity v2 is nothing but u1 minus u2 plus v1. This is from elastic collusion in one dimension, right? We got relative velocity before and after collusion is actually same. So from there we got v2. Now substitute v2 in this equation. So we have m1 u1 plus m2 v2 u2 over here, which is actually equal to m1 v1 plus m2 into, instead of v2, substitute this terms in the equation, that is u1 minus u2, okay, plus v1. Now now what you have to do is try expanding these terms over here. We will get m2 into u1 minus m2 into u2, okay, plus m2 into v1. Now on the other side we have m1 u1 plus m2 u2. Now what we would do over here is, let's take, okay, let's take, if you see here we have m2 u2, here we have minus m2 u2. So let's take this term to the other side, right? So if we take this term to the other side, let's see, we have m1 u1 plus m2 u2. Let's take this term to the other side, so it becomes plus m2 u2, which is equal to m1 v1 plus m2 u1 plus m2 v1, right? So this term over here, if you see, m2 u2 plus m2 u2, so you will end up getting 2 m2 u2 over here. Okay, then what we have is m1 u1. So what we will do on this side is, let's take u1 to the same side. Okay, so here if you see, we have m1 u1. Let's bring this to the other side. We have minus m2, okay, m2 u2, okay, sorry, minus m2 u1 over here. This term we are bringing to the other side, u1 plus 2 m2 u2, which is equal to m1 v1 plus m2 v1. Now what we are going to do, let's take the m1 commonly outside over here. So we get m1 minus m2 into, let's take u1 commonly outside, u1 plus 2 m2 into u2, which is equal to, here v1 we can take commonly outside, we get m1 plus m2. So from here if you see, v1 is nothing but m1 minus m2 into u1, okay, plus 2 m2 u2, okay, the divided by m1 plus m2, Okay, obviously you can divide it for individual terms, right? Instead of dividing it by whole, you can divide by individual terms over here. This will be into m1 plus m2, right? Then this is again divided by m1 plus, both sides you can divide by m1 plus m2. So this gives us the equation for the velocity in of the object v1 after collusion. Okay, v1 you can, if you know mass of both the object and if you know initial velocity of both the object, v1 can be calculated. Then just change the subscript over here. In the previous case, what we did, we substituted in this equation for v2, right? Now substitute in the conservation of linear momentum equation for v1, you will actually get the value for v2 over here. Or what you can do, just change the subscript over here. Wherever you see 1, write 2. That's it. You will get the velocity of the second object also, and always velocity of the second body, that is b, velocity after collusion for object B as well. Okay, so from this gives us the velocity after collusion, what is v1 and v2, can be found using this formula. Alright, so with this note, we are coming towards the end of today's class. So if you see in if you go to the Unacademy platform, okay, go to self-study, click on free live classes. There will be n number of free live classes available for you guys. Say in the free live classes, they would be check out the upcoming free live classes. There would be a class again for collusion as well, where we will in depth discuss about the numericals and also what are the special cases with respect to one-dimensional elastic collusion. Alright, so with that note, I am ending today's class. So if you like the class, do share it among with your friends and subscribe to the channel. So before any class goes live, click on the bell icon also. So before any class goes live, you can actually get the notification. Now other than this, if you go to just that app as I said, and if you click on self-study and free live classes, there are classes for other we are covering other units also on the platform. Those are completely free classes. You can actually enroll for the same as well. Alright, and see you all in the next class. Bye, take care.